All right, reaction mechanisms. The reaction mechanism is the actual pathway that reactants follow to get from reactants to products. Okay. A reaction mechanism can be very, very simple, just A to B, or they can be very complex. This over here at the right is the proposed reaction mechanism that takes place when acetylene is combusted. Acetylene is a very simple molecule, C2H2. If it were, not an old name that people just sort of like, then it would just be ethine. It's a carbon-carbon triple bond. It's a really high energy molecule. You get tons and tons of side reactions and byproducts, and it's just C2H2 and O2 reacting to make CO2 and H2O. And yet, this is the god-awful mess that results. We won't be trying to figure out a reaction mechanism like this. We will be dealing with far simpler sorts of pathways. Nevertheless, they can get quite difficult. But maybe looking at that god-awful monstrosity there on the right, maybe you can see where you might get half orders and things like that from. Let's take a step forward and a step back. Let's just take a step away. Let's back away slowly from that. Oh my God. All right. Elementary reactions. Sorry. Elementary reactions are very, very simple reactions. This is the only time where the rate law is based on the reaction coefficients. Okay. So you can have a unimolecular, bimolecular, or very rarely a termolecular elementary reaction. For a unimolecular reaction, you just have one molecule, A, turning into B. Or it could be B plus C or whatever. But the point is you start with one, and the rate is just K times A. For a bimolecular reaction, you have two molecules coming together, so they could be 2A going to B, or A plus B going to C. So the rate would be equal to Ka squared or Kab. Nice and simple. Termolecular, you have three molecules coming together, which is why it's so really, really, really rare, okay? Because we're talking about things randomly bouncing around in space. Having two molecules collide, not so rare. Having three collide all at once is very rare. So it could be 3A or 2A plus B or A plus B plus C. So that would be Ka cubed or Ka squared B or Kabc. But those are the elementary reactions. And when you come up with an actual reaction mechanism, what you're doing is you are adding together elementary reaction steps, multiple elementary reactions to get the overall reaction mechanism. There are some reactions out there that are in and of themselves elementary reactions, but those are fairly uncommon. Most reactions are a little bit more complicated. So let's dive into the muddy waters of the reaction mechanism. Okay. Now, a reaction mechanism is a collection of elementary steps that is proposed as the possible mechanism for a given reaction. Okay. So for any proposed mechanism, all the steps have to add up to the reaction you're looking at. Whatever way they add up, looking at the rate of each individual step, you have to come up with the same rate law as the actual rate law you've measured. And that is where things can get really complicated, thanks to equilibrium reactions and slow steps and fast steps. For this course, I've decided to go ahead and keep it simple. At the moment, we are only going to be looking at straightforward reaction mechanisms. We won't be diving into equilibrium reactions and things like that yet. They can make those things very complicated, as you'll see in the textbook. But for the moment, we'll keep it simple. So let's go ahead and look at an example of a reaction with a rate law and some proposed mechanisms. So here is our example, or just our little example. 2A plus B goes to form C plus 2D with a rate law that has already been measured and determined of KAB. And we have three proposed mechanisms down below. Each one has multiple steps. Each one has slow and fast steps. And we get to test each one to see if it could be the actual mechanism. Okay? So mechanism 1 says 2A go to form E. That's an intermediate, and that's our slow step. Then A and B react to form C and D. Then B and E react to form A and D. It's perfectly fine to have something show up in the mechanism that does not show up in the overall equation. That's not a problem at all. Intermediates are they're a fairly common thing. Okay, I've already made I've already made this problem fairly straightforward because the slow step is right up top. You don't have to worry about combining multiple steps to find out what the actual rate law should be for that mechanism. This is a very simple sort of problem. So our first step is we add them all together, for each of the proposed mechanisms, we add all the steps together to compare them to the balanced reaction. Okay, that means they have to add up to the final reaction we're looking for. Sort of like a Hess's law problem, if you remember that from your first semester of chemistry. So let's look at reaction mechanism 1. Our intermediate E will cancel out. We have one on the right, one on the left. They cancel out. We have an A on the right. We have several A's on the left. Those will cancel out. And when we add those three steps together, what we get is 2A plus 2B goes to form C plus 2D. That does not match our actual balanced reaction. Okay, 2B, no good. So this is out. It's gone. Okay, that mechanism failed the first test. Now let's come over and look at mechanism 2. Okay, A plus B goes to form E. That's our slow step. A plus E goes to A plus E goes to form C plus 2D. Sorry, anyway, that adds up all together. The E's cancel out to form 2A plus B goes to form C plus 2D. Booyah! That works just fine. Now we come to mechanism 3. 2A goes to form 2C. That's a slow step. Then B plus C goes to form 2D. One of our C's cancels out, leaving us with the overall of 2A plus B goes to form C plus 2D. And that also matches our actual reaction. So reaction mechanism 3 also passes the first test. Okay. So that's why we need multiple tests, is something that you can get. Each of these matches the actual balanced reaction. That doesn't mean that they match the proposed rate law, though. So let's go ahead and clear out some space and look at our second test. So we will now compare the two remaining mechanisms to the actual rate law up here on the right, KAB. Let's go ahead and clear off some space and move this over. Okay, so each of these has a slow step and a fast step. The slow step is the one that matters for the rate. You can only go as fast as the slowest member, right? Like if you can imagine 5 cars waiting at a light, the third car is just sort of sitting there. The first 2 cars are going to go, no problem. The other 3 the 2 cars at the back have to wait for the third guy to, look up from his phone, jackass. Okay, so we look at the slow steps to determine, because the slow step is the rate determining step. All right. Now, because a reaction mechanism is always made up of elementary steps, each of these steps has its own rate law that you can get just by looking at at that step. So, for reaction 2, or for mechanism 2, the rate determining step, the slow step, would have a rate of KAB. And boom, okay, that works just fine. That matches the rate law. And come over here to reaction mechanism 3, and the rate determining step gives us a rate of Ka squared. And that does not work. It just doesn't match the proposed rate law. So we have a mechanism, a proposed mechanism that works. Mechanism 2. A plus B goes to form an intermediate E. Then A plus E goes to form C plus 2D. Okay. This matches the balanced reaction, and it matches the experimentally determined rate law. But is it correct? Maybe. A proposed mechanism may be consistent with a reaction without necessarily being the actual mechanism for the reaction. In this case, if I wanted to test this experimentally, I would go in the lab, set up the reaction, and look for the presence of the intermediate E. Maybe it's reactive in some way. Maybe we could set up another reaction that would siphon off E as soon as it was formed to prevent the formation of C plus 2D, right? Or maybe you could test for it with spectrometry or something like that. You know, just any, there are lots of possible ways to test for the presence of E. In any event, what you're finding here is not necessarily the actual mechanism. What you're finding is the proposed mechanism consistent with the experimentally determined rate law? Okay. All right, and that will do it for Chapter 12. See you again in Chapter 13.